Today we start talking about derivatives, which I would say is really where the pre-calculus stops and the calculus actually starts, right? So now we've been introduced to the notion of derivative. We really are starting calculus. In particular, we now have the idea of a derivative as a function instead of just a number. In the previous homework set, we were just thinking of the derivative as the slope of a tangent line. But now we sort of recognize the fact that this tangent line could have been drawn anywhere along our function. And so we sort of have like an input, which is where on the number line we draw the function. And then the output would be the slope of the tangent line. And we can just package all of this data together into a new function, a brand new function, which we now call the derivative. Okay. And the only difference is just in the limit definition, we no longer are dealing with a number. So let me show what I mean. So we're going to see this with the first two problems. First of all, we would probably want to extract out the function that we're trying to take the derivative of. So f of x in this problem, number one, is this x to the negative first power. Okay. The limit definition, accordingly, is f prime of x is equal to limit as h goes to 0, f of x plus h minus f of x all over h. Okay, and the key difference between previous homework and the current is that this is an x, not as in the previous a. So in the previous, we had a being some particular number, but here we now have just a variable x. And so what we get out, we expect to be a function rather than just this constant, this number. Okay. But overall, this process of using the limit definition to find the derivative, it is exactly the same, right? There's a little bit more algebra involved since we have less numbers and more variables. But otherwise, the process is entirely the same. So for this, we have to plug x plus h into our function, 1 over x. I'm going to reinterpret this as 1 over x. And then minus 1 over x all over h. And I think it's pretty clear what we have to do from here. We need to cancel off these extra denominators. So we go ahead and we multiply by x plus h times x, and this will cancel off the two denominators. And of course, we have to multiply both top and bottom by this. Okay. Now we can go ahead and write down what it simplifies it to. So this will become x minus x plus h all over h times x plus h. And there are some simplifications. So x and minus x will cancel. That's the first thing. And I'm going to save space by also mentally doing what the second simplification is. So note that like at this stage, our numerator is now negative h, and we have an h on the denominator. So we can cancel these two. And I'm going to use a different color, but it might not show up so easily. So we then divide top and bottom by h, and then the numerator is now a negative 1. Okay, so now we can write down what this has become. Negative 1 on top over x times x plus h. Okay, and then we take the limit. So that's going to turn into x times x, or x squared. Okay, and at this point, I'm also going to say how we could check these kinds of calculations. So part of this week, what you cover are actually some of the basic derivative rules. And so I'm going to introduce the power rule to you. Hopefully you've like gone through the videos and gone through the slides and you've seen all of this. So hopefully this isn't the first time you're seeing this. But there's a power rule which says if you're trying to take the derivative of x to some number n can be an integer, it can be a rational, meaning a fraction, it can be a real number. This rule applies in all those cases. It's n times x to the n minus 1. Okay, so you have to remember that you bring that number down as a coefficient in front, and that you subtract 1 from it afterwards. Okay, and you're always subtracting 1. All right. So notice that for this problem, what I'm going to do is I'm also going to introduce my notation for a derivative, which is just an arrow with a d on top. So this just means derivative. It's just a nice shorthand. If you apply the product rule to this, you'll get minus 1 times x to the negative second power. And if you remember your exponent rules, you have that this negative exponent is the same as putting it into the denominator, reciprocating it. So you end up with an x squared in the denominator. So these two things are equal, and so we verify that our algebra works out. Right? But I should, I guess, emphasize, like, the problem does say use the limit definition. So just using this power rule trick, well, no, it's not really a trick, but just using power rule is not going to get you any points on this problem. You are supposed to use limit definition to work out this problem in full. Okay, any questions so far? If not, we'll keep going. So number 2, we have a different function, square root of x, and we go through the same process. So let's extract out what is our function. It's square root of x. And we are trying to take the derivative, f prime of x. And the limit definition is limit as h goes to 0, f of x plus h minus f of x all over h. Okay. And now we go ahead and we plug in. So x plus h, if we plug that in, that's basically what this step entails. So when we plug it in, we get square root of x plus h minus the square root of x all over h. And hopefully it's clear what we want to do as our next step. So I'm going to ask you guys, what do we do?
We multiply it by the opposite, right?
There's a better word than opposite.
Conjugate.
Conjugate, that's right. Conjugate. Yep. So conjugate is going to be x plus h. And then the opposite, you take the opposite sign. Yes. So it's always nice to, like, know what the words are. It's like if you're trying to explain it to your friends, say, right? Like, say that they need help on something and that you're trying to talk them through it. It's good to know the terminology. All right. So yeah, there we go. This is the conjugate. We're multiplying top and bottom by it. This will help simplify things out. All right. And so now we just write down how it simplifies. So this is going to turn into x plus h minus x. So the conjugate, what it does is it squares away these square roots, and it also doesn't introduce any middle terms. So in effect, I'm going to put these parentheses that I normally wouldn't, but this is just to illustrate my point. So the x plus h in the square root, that gets squared, and so the square root squares away. Maybe I should make that look like an h. Yeah. And so does the square root of x. That also gets squared. And so then the square root gets squared away. Okay, and then the denominator, well, that sort of remains a mess, but we'll see that it's not such a bad mess. Okay. Right, and now let's see, things cancel. So x and minus x, and also h and h in the denominator, right? So when you so I'm gonna combine two steps in one. The h and the h in the denominator will cancel. And you'll have limit as h goes to 0. These should look like arrows. H goes to 0 of 1 over, and then we've got square root of x plus h plus the square root of x. Okay, and now we take the limit, and then this term in the denominator turns into square root of x, which will double up with this. So when we take the limit, we get 2 square root of x. Okay, and now we can double check our work. So the way that we double check, again, is we use power rule. That's what we would want to use. for this problem. And so you have to remember that the square root is actually just a 1/2 power. Okay, so we can rewrite square root of x as x to the 1/2 power, and then we can take the power rule. So we take the derivative using power rule, and that's going to bring the 1/2 out, and we will subtract 1 from the power. So 1/2 minus 1 is this guy. And you can check that this negative just means it's 1/2 power in the denominator, which is precisely that. So maybe I'll start to use a different color just. So we do actually get that this result we get from using power rule is the same as what we would get through taking the limit definition. So everything checks out. Okay. It's always good to be able to like check your work somehow. So I like to explain that. All right. Any questions so far? If not, so number 3, all we need to do with number 3 is basically just use power rule a couple times. So I guess the one thing to note is like you really don't want to deal with x in the denominator. You anytime you see that, you kind of want to bring it to the top with a negative power. So I'm gonna start by just rewriting this like so. Okay, so just to remind myself what that is, and then we use power rule. So these are just practicing using power rule. All right, so what is the derivative of this first guy? So maybe I need to remind you what power rule is. Let me rewrite power rule. N times x to the n minus 1. That's what happens when you take the derivative. You can type it in chat if you want to, but is everybody lost?
Yeah, I'm a little lost.
You're lost. Okay. All right, so I got yeses. I got yeses from a bunch of people. Okay, that's I wasn't expecting people to get lost. Okay. So right, first of all, you have to remember this rule. Okay, I see. All right. Right. So people are suggesting 15x squared, and that is the correct answer. But I guess maybe I need to step through it a little bit. So let's go off to the side and let's recall power rule. So power rule says x to the nth power, when you are asked to take the derivative, it's n times x to the n minus 1. Okay, so let's look at some examples of this. What happens if we take the derivative of x squared? Well, we dropped the 2 down, so we have 2 times x to the first power. But we would never write it as that. We would just write it as 2x simply. Okay. What if we have an x cubed? What is its derivative? Well, according to the rule, we bring the 3 down and we subtract 1 from its power. So we get 3x squared. Okay. So for this first term, 5x cubed, we do get 15x squared. Okay. The one thing to note here is when you're taking, so this is another property of derivatives that, did we introduce it previously or not? I don't remember. The idea is if you have a number in front, like a number that's just scaling the whole function. So like if you have like 5 times f of x and you're taking that derivative, that's just equal to 5 times f of x. Like you can pull constant multiples out of the derivative. So that's what happens with this 5. So when you're taking the 5x cubed and you're taking its derivative, that's going to be 5 times the derivative of x cubed. And then the derivative of x cubed is just 3x squared. So then you have 5 times 3x squared. And so then you multiply the 5 and 3, you get 15. Okay, so hopefully you're not as confused. This next term, right? So again, you want to use the product rule or the power rule on this. So what you would do for this, I guess I'll write this off to the side, 2x to the negative third. If I take the derivative of this, just using the power rule, well, the 2, we sort of move that to the side and we deal with it later. We consider the derivative of x to the negative 1/3, or x to the negative third power. And the power rule says we bring the exponent down and then we subtract 1. So bringing the exponent down, we get negative 3x, and then we subtract 1 from the power, so we get negative 1/4. Okay, so this is spelling this out in a lot more detail than I normally would. And so then you see that you have to multiply these things together and you get negative 6x to negative 4. Okay, so is everyone following so far? I haven't lost anybody, hopefully. The last term, notice that this is a constant. Okay, good, thank you. So yeah, so notice this is a constant, right? This doesn't depend on x, this is just some number. And what happens when you take the derivative of a number? Well, the answer is you get 0, okay? So I'll make a comment. I'm not gonna write plus 0. I'm just gonna say this becomes 0 for this term. And one way you can think about it is a constant function, right? So like think of the function 2. 2 is just a function. It's a horizontal line. You would just draw like the line y is equal to 2. It'd be completely flat. And so if you ask like what is the derivative, what is the rate of change? Well, it doesn't change at all. So change is 0, the derivative is 0, 0 everywhere. So derivative of a constant is always 0. Okay. So we would get this for this answer. I'm gonna try to go a little bit faster because I hopefully like well, if you're sort of if it's taking a while for it to click, then the best suggestion I can give is to just practice a whole bunch. There's definitely sites out there that you can use. I think Khan Academy you can technically use, like it has it will like generate problems for you to practice with. So you could use that to actually like practice your derivative process, or you could use a black pen, red pen. Also has worksheets that he sort of works through. You could just follow along and practice. Like ultimately, derivatives should be a pretty mechanical process. Once you just get used to the formulas, it's just sort of cranking it out. It's a very robotic kind of thing, actually. So let me just go ahead and do this. So derivative of this, 7 times and then 3/2 t, and then you would take the 3/2 and minus 1. So this is where you have to know like how do you subtract 1 from a fraction, which surprisingly enough people will mess up on sometimes. So just make sure that you can subtract 1 from a fraction. So you would get 1/2 for this. And then this is minus 6. If I bring this down, I'm going to get negative 3/2. And then t to the, I subtract 1 from this, I get negative 5/2. And I wouldn't write it like this. I would combine these numbers. So we'll get 21/2 t to the 1/2. And then you see that 6 divided by 2 is 3. You'll get plus 9 t to the negative 5/2. All right. Good so far? Any questions? Okay. might not get as far in this class as the other one. We'll see how that goes. Okay, so number 4 is actually somewhat tricky. There's a technicality to it, but 4a at the very least is straightforward. So it's just limit definition. So we just run through the same process. So let's just quickly recite how that works. This time around, the variables are slightly different, right? Instead of f of x, we're having y of t. So I'm going to rewrite. I'm going to use the variables that are given. Oh, that should be an h. So limit as h goes to 0, and it'll be y of t plus h minus y of t all over h. And we're just going to plug in. So, well, limit as h goes to 0. This is kind of a pain to write. T plus h squared plus 50 t plus h plus 5 minus, and then y of t, I can just blindly copy y of t because that's what's given to me. Okay. And this is all over h. Right. So I think just to, I'm going to cancel the 5 and the minus 5. I can also cancel the 50t and the minus, well, 50t here and minus 50t there. And then we're going to expand this out. I'm just doing this to save a bit of space. So when we expand this out, we get minus 16t squared plus 2th plus h squared plus 50h. And the very last term we've got here is a plus 16t squared. And this is all over h. And note that we can cancel the minus 16t squared with the plus 16t squared. And the remaining 3 terms all have h. So we can do a bit of mental arithmetic and distribute this and cancel h at the same time. Right. Again, just to save a bit of space. So minus 16 times this 2th divided by h. That's what I'm first thinking of. And we get a minus 32t. And the next term is minus 16h squared divided by h minus 16h. And then the last term is this 50h over h, which gives me 50. And I can now take the limit. So that's going to make this term disappear. And we end up with minus 32t plus 50. And I can box this guy. So this is what we expect also. Note that this is exactly what we expect because we can just take this formula and we can just take its derivative using power rule, right? So power rule would just say bring the 2 down, so you get minus 32t. And then this, when you take its derivative, the t just becomes a 1. T becomes 1. And so then you get 50 times 1, which is 50. So you do get this. Okay. Now things get a little bit more involved when we start doing part B. So I'm going to start introducing this technique of using a number line and dividing it up into intervals, because this is what you'll be doing later on when you do this section on curve sketching. So the technique is, if you want to figure out these intervals where it's positive and where it's negative, you kind of want to start by finding when is it equal to 0, because these will serve as natural boundary marks for the intervals where they are positive and negative. So we really want to solve when is y prime of t equal to 0 first off. And so that, when we just plug in what is y of t in this problem, we get minus 32t plus 50. We want to set that equal to 0. And we want to solve this guy. So that, I'm just going to do that mentally. We'll have 50 divided by 32, which is going to simplify to 25 over 16. And you could kind of write seconds because it does have units. This problem is in terms of feet per second. So we can put seconds there. Okay. So how does this help us? Well, now we can mark our number line. 25 over 16 is our sort of our boundary. Oops. And this, we want to think of this number line as sort of encoding the information for y prime. So at this point, it's equal to 0. What about these two intervals? So now we look back on the function that we're working with, which is this, well, this box function here, minus 32t plus 50. Okay, so if we plug 25 over 16, we would get 0. That's what this analysis has told us. What happens if we plug something that's greater? Well, the negative is going to dominate. So we would get negative for this. See, I don't need to plug numbers in for that one. What about when it's over here? Well, we can do an even faster thing. We could just notice that 0 isn't here. We can just plug 0, we get 50, so positive. Okay, so this gets us close to the answer. You could say from this that like it's positive from minus infinity to 25 over 16, negative from 25 over 16 to infinity. And there are some technical reasons why this is not entirely the case, right? So coming back to the problem, note that we're actually dealing with a real world problem. And the thing even tells us like, oh, the ball's going to hit the ground. And also, we're sort of measuring time starting at 0. So we actually have a boundary here, and we have a boundary here when the ball actually hits the ground. So this kind of complicates matters. Okay, so to really answer this question, we don't want time to go to minus infinity or to plus infinity. We want to figure out, well, this endpoint. Okay. Why did I hear something? And that endpoint is when the ball hits the ground. So
Wait, I had a question.
Yeah.
So you said that the ball starts from 0. Wouldn't it start from 5?
The height.
Yeah.
Yeah. So the height starts at 5, but the time that we start measuring is
Oh,
t0.
okay. Gotcha.
Yeah,
Gotcha.
that's the difference.
Oh, okay.
Yeah.
I understand what you're talking about.
Mhm.
Thanks.
Yeah. Okay. Don't know what's happening outside. I'm hearing noises from outside. It's really irritating. Anyway, right. So what we need to do is figure out when does the ball hit the ground. So maybe actually, it's probably better for me to just continue writing this off to this side. So when does the ball hit the ground? We need to answer this question in order to figure out this point, this right endpoint. So in math terms, this is saying when does this, well, solve? It translates into solving y of t equals 0, right? And notice that y of t is what we would call quadratic. So I'm going to ask you this, and hopefully you guys can answer. How do we solve this kind of equation? How do we find when this quadratic is equal to 0? Anybody?
Do you make it equal to 0?
Uh,
The original?
well, I set it up as in that way already.
Oh, okay, then never mind.
So I'm saying set it equal to 0 and solve it. How do we solve it? What is the process to solve it? And someone answered me from, I guess, from a private message, and they got it right. So that's good. That's promising because my other class they were completely silent. So yes, the answer to how do we solve this is we use a quadratic formula, right? So using quadratic formula. The reason we can do that is because this is a quadratic, right? It's to the second power. So I guess just like before, I'll have to recall what is quadratic formula. So quadratic formula, what it does, where did my cursor go? How does this guy work? So the idea is that for a general quadratic, for any quadratic, and by quadratic, this is what I mean. Y is equal to ax squared plus bx plus c, right? A, b, and c are just numbers. We can choose any numbers for this. The roots, so this is what the quadratic formula finds for us. The roots are given by x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. This finds you the roots, which roots, I hope you understand, are when the thing equals 0, right? Roots are these 2 points where the function crosses the x-axis, which is the same as saying when it equals 0. Okay, so this is just when it equals 0. Okay, so this finds you those x values. And so for this problem, we're looking for when is equal to 0. We're looking for the roots. So we have to use quadratic formula to do it. I'll say that, like, for nicer situations, you don't need to use quadratic. You hopefully remember this thing of like factoring the polynomial, and from the factorization, you can actually just read off the roots. But here, actually, this doesn't factorize, which is kind of irritating. So this guy doesn't factorize, and so the way that the roots look is actually pretty horrendous, I would say. I'm going to write down what you will get if you plug it into a calculator. You could also do it by hand, but I mean, it's a computation that's a bit of a pain. So you'll get this if you plug it into a calculator. This is going to be that root there. And I'll say this is approximately, a little bit more space, 3.22199. And this I would measure in seconds, because this is the axis here is actually time. Yeah. Okay, so that's that endpoint. And so now that we have these endpoints figured out, we can write when is it greater than 0, when is it less than 0. So we can come back to answering this question. For t in the interval, so greater than 0 is going to correspond to this left half. So from 0 to 25 over 16. I'm going to use open paren because I don't know, it's a bit strange to consider like at 0 precisely what is happening, because it's sort of like immediately starting up. So I'm just going to exclude the 0 in this case. And then when is it less than 0? That's t going from 25 over 16 up to whatever the decimal was, 3.22199. Okay. So now this is the more technically correct answer, instead of saying that time goes to infinity to minus infinity. Yeah. Okay, any questions on that? Okay, then for part C, over what time interval is the ball going upward and going downward? So C is just reinterpreting B, but instead of these labels, we're saying like when is it going upward versus downward. So you should understand, like, intuitively, y prime, so y is the height function, it's measuring the height of the ball. Y prime is the change in height. So if we're saying that the change in height is positive, that means that the ball is going upward. If we're saying that the change in height is negative, that means that the height is decreasing, so the ball is going downward. So we really hard just relabeling this. So upward and downward, and the answers are the same. I actually wrote them in the same order also, which is good. Okay. For D, we want to figure out when does the ball reach its maximum height. So for this, I want to look at this diagram. Okay, so maximum height. So what this diagram is saying is that at all of these points in time, the height is increasing still. Right? Y prime is positive, the height is still increasing. At this point, the height is stationary. It doesn't change for just a split second. And then after that point, the height starts to decrease. That's what the negative means. So that tells me that this precise point, which remember that this, how do we find this point? We found it by setting y prime equal to 0. This is a common trend that you'll see happening in calculus. Setting the derivative equal to 0 and solving, in this case, is giving us a maximum. It can also give you a minimum depending like on your actual function. So it will find maximums and minimums. Okay, so right. What I'm to answer this problem, when does the ball reach its max height? At the time in that written there. So t is equal to 25/16. And for this, we should probably write seconds. Oh, I even wrote down what the decimal approximation is here. I didn't realize 1.5625 seconds. If you like decimals, that maybe that'll make you happy. That's a 6. Okay. Max height. When is it, or what is the max height? So hopefully, like you can piece together. We have this y function. This y function gives you the height, right? And we know what time the max height is achieved. So all we need to do is plug that time into that function. So we would plug in 25/16 into y, and it's a bit terrible to do this by hand because you have to square it and multiply it by 50. So yeah, I'll say I definitely use the calculator for this, and that's okay because these numbers are terrible. But theoretically speaking, you could do this by hand if you really were pressed to, right? And so what is the decimal value for this? 122.1875 feet. I haven't boxed any of these, but I would probably just box these. Okay. Any questions on this problem? Everything makes sense? There's 10 minutes left. I might be able to do number 5, but I won't be able to get to 6, I think. Okay. So, right. So if you read this problem, the main statement is here. If you price whatever your download is at C cents, then your song will be purchased this many times. And you want to create a formula for revenue. Okay. So you should understand like from like an intuitive real world kind of thing, that revenue is going to be the product of these two things. Like how many times your thing gets purchased times how much you're paying for that purchase. So it's going to be C times 5,000 minus 100 C. And in order to make it easier for our next step, we want to actually distribute this. So 5,000 C minus 100 C squared. Okay, now we just take the derivative. And so that's just an application of the power rule, which we talked about in the previous page or so. So then this is minus 200 C. Okay. And then for part C, we want to do kind of the same analysis as the previous problem. So we want to figure out when is r prime equal to 0. So R prime of C equals 0. When exactly? Well, first let me translate that to this problem. 200C. When is this equal to 0? So I bring the 200C to the other side. I divide by 200. And I'm going to be left with C is 5,000 over 200. And now we just cancel off some zeros. We get 50 divided by 2. And that's 25. And I'll remark that this is measured in terms of cents. So this is 25 cents. Okay. Then just like before, we can, maybe I want to put the number line a little bit, maybe over here. So we've got the 25 cents here. This is showing what the change of the revenue function is going to do. So we look at this guy and we think, okay, if we plug in 25, this would give us 0. That's what this analysis has told us. And what happens now if we put in something that's greater than 25? Well, the negative part is going to dominate. So this will become negative. What if we plug in something on this side? Well, then it's positive. You could just consider plugging in 0. Okay, great. And that translates directly into this. Well, we should notice this. So notice this guy. That actually gives us the cutoff. So this is a lot nicer than the previous problem because we right away get these real world cutoffs on this number line. Right? We don't expect the price, the C, to be outside of this interval from 0 to 50. Great. So we can now write when these two things happen. R prime of C is less than 0. And so this is from C. So we're talking about greater than 0. We're talking about the positive part. C in the interval from 0 to 25 open. And when is it less than 0? C in the interval from 25 to 50 closed. So note that I'm not using the same set of brackets, right? I'm using a square bracket and open or paren. The reason for that is because I can actually put the endpoints in for this. So I can plug in 0 into R prime and I do get a positive value. So I do include 0 here. And for this one, I can plug 50 in and I will get into here and I will get a rather negative number. And so I do include 50 in this answer. But if I plug 25 into R, I get 0. And so I exclude 25 from both of these two. Right? So it's a rather technical, rather subtle kind of thing. I'm writing it there just to be technically correct. Okay. So that's C. And now D, interpret the meaning of part C. What should you charge per download if you want to maximize the total revenue, and how much total revenue do we generate? So maximizing total revenue is again coming back to like just considering this diagram and noticing, so up until 25, the revenue is increasing. And then over here, the revenue is decreasing. So we hit a max at this 25. So that answers the first part of this problem. To maximize, if you want to maximize revenue, you should charge 25 cents. I guess you could say per download. And how much total revenue will you generate? So that is going to be gotten from plugging this 25 into the revenue function. So total revenue will be R of 25. And we can go ahead and compute this. So in this case, the function isn't so bad. We can actually compute this by hand. I'm looking at, which one am I looking at? I think I'm looking at this one. It's easier to do this one, I think. 25 times 5,000 minus 2,500 So inside we have a 2500 times a 25. 25 times 25, you might know is 625, and then you tack on 2 zeros. And this is somewhat crucial. What are the units here? Right, so you should definitely be thinking to yourself, what are the units of this? And you should recall that this thing that we plugged in is cents. So this is also in cents. I missed. This is cents. Okay. And so if we want to convert this, we would say we would convert it to dollars. We get $625. Okay. So that is part D. I'm not going to have enough time to go through this. I went through like 2 of them in the other one. I'll just mention that you should look at the product rule and quotient rule, and maybe I'll quickly write them. So product rule. So for the product of 2 functions, you would get f prime g plus f g prime. I'll do like a mini lecture before we start like next recitation. And for the quotient rule, but you can also like see this in Craig's lectures that he's posted online. Quotient rule, it is f over g, take the derivative, it's f prime g minus f g prime over g squared. So it's a really good idea to get to memorize these things as quickly as soon as possible, because we're going to be using these derivative rules pretty often. Like I would say the first half of calculus is going to be focused on derivatives and derivative rules, and then the second half is going to be on integrals, and it sort of has rules as well. So the sooner you get used to these rules, the better, and we'll be working with them for the rest of this problem set, I guess next time. Okay, so I guess I'm done talking. Are there any questions?
I don't have a question on the math, but you asked a while back about if there was like a Discord. Did you ever find one?
Oh, I haven't heard back from anybody.
Okay.
Yeah.
Okay, thanks.
Yeah. I mean, I would consider creating one, but I definitely don't have time to manage that. Somebody should make one, I think, just to help everybody out. But